Morning, everyone. Thanks for stopping by or staying. So the last is for the better, so the better is for the last. So let's go for the best. First of all, I have to say that this work was jointly done with my student, Fabian Perez. Super smart guy looking for internships. So if you like this job or this work, please reach out. He's actually currently in Colombia and is an undergrad student. So let's show. So our work is called Beyond Appearances, so material segmentation with embedded spectral information from RGB-D Imagery. So first of all, I want to introduce like what material segmentation is. So we can see here like most of work on segmentation is mostly on semantic segmentation. So we have like a motorbike there and maybe some like background information, but we are interested on material labels. So here we have like paint and concrete, some asphalt or plastic or different classes. This has been used recently a lot, and one of the goals is to have like a richer segmentation map, also dense map, but a richer segmentation map that can actually help us like not just tree and cars, but we have also like actually have leaves and trunk and like different classes in here. It will help like different application, like in autonomous driving, you can actually try to recognize like what kind of road. So we have like concrete or segment, or we have like any different materials, open road. So that's one of the useful applications. Also for realism, now rendering and all these different like trying to create like synthetic scenarios. You can be like more basically have more realism on like those scenarios. And also for navigation, like you have a robot or something similar, like you want to teach the robot how to interact with objects. So if this is wood or this is plastic or this is like metal, how do you like hold things? So this is different. So that's why it's important to know like what kind of material is you're interacting with. So also like on a side fact is like a depth estimation is also useful for navigation, not just the material. So that's why we delve on trying to this latest network from, I guess it's Apple, that they train with a super big data set and just like a monocular depth estimation network, you can have a like depth map, super nice depth map and with point clouds. But for this work, we actually rely on like off-the-shelf RGB-D data. So we want to democratize somehow the need of how can we do material segmentation, but with like off-the-shelf devices. So we will show a cool demo at the end of the talk. So for now, the general approach of material segmentation is relying on RGB images. However, we have a metamerism. For those that are not familiar with metamerism, like different materials can look the same to your naked eye. So for instance, here we have checkerboard, but these are different materials like in the shoe or in a belt. So how do you differentiate these different patterns, although it's the same pattern to your naked eye? Also, a more challenging scenario when you have plastics. So all these are same material on the right, but it's just like different colors. So maybe you can be fooled with the different colors or shapes, but the material is important in this to basically check like, yeah, these are exactly the same material or same class of material. So with this in mind, one of the key components and actually what we exploit and my experience is about spectral information. So spectral information is some sort of a fingerprint of materials on nature. So you can see that we have different materials here, just for example, 4. So brick, stone, wood, and marble, although they are like different stones or kind of different materials, you can see like they behave differently when you just have not just 3 points like RGB image, you have a red, green, and blue channel, but you have a collection or spectral signature of that. So how can we actually measure spectral information such that you can incorporate that to your like device? So based on that, we actually propose this architecture. The RGB-D image pair is the input to a encoder-decoder architecture, which basically is trained end-to-end to have some sort of a spectral features. But this feature entered to our proposed model, the spectral feature mapper, which basically uses a spectral data set to basically do some sort of attention mechanism for basically see these output features actually correspond to some like consistent spectral mapping. But one of the things that I want to stress is like spectral information is just required for training. So we can do this offline and then like release our stuff, and we will just rely on RGB image for like evaluation period. So this output of SFM will go to a softmax, and then we will have this segmentation map. We use this different like a composite of segmentation and reconstruction loss functions, but I want to stress out like we rely a little bit more on the, we weighted more the segmentation loss. Delving a little bit more on the SFM module, let's assume we just take one of these pixels. So a pixel of this cube is actually a spectral signature. The SFM module, in short, will compute the cosine similarity between the actual signature and what's learned. And depending on that, we will basically have this like negative sign on the cosine similarity, because closer to zero means more like similarity. So that's why we have the negative in there, such that after the logics go through the softmax, so we have like a segmentation map, like a binary segmentation map for each one of the classes for all the like height and weight of the image. So yeah, that's the proposed framework. So as I said, you will have just a RGB or even RGB-D sensor. The measurement will go to the encoder decoder, and the trained SFM layer module that will be available will basically decant on this material segmentation map. Plus, given that we have the depth image, we can sort of do the 3D like point cloud, and yeah, that's the goal. So just to show, sorry, I am running out of time. For the segmentation loss, we use the focal loss. For reconstruction, the NSE. These are the actual training parameters if you want to see more about those. And these were like results with state of the art. So this paper in 11 use the unit or the FCN, and our results are pretty much better. So we can discuss more details in the poster session if you want, but these are just special reconstructions of that. We also tested with real world experiments. So we took our iPads and went outside of our building and acquired some data. We used the AR Kits SDK from Apple to access the data. So it's very somehow difficult to access the data, like raw data. So we actually had to do it with the AR Kits and try to basically know this 32 by 32 point cloud data from the iPad. So we went outside of our building. These are just like example of that. So the data set that we use is just for packets. So that's why we are constrained somehow to packets. So I mean, like we have some like bricks with some trees or some different classes, and these are like real data. We have RGB-D, and these are the segmentation and the point cloud result with that. So just takeaways: the spectral feature mapper is the model we propose. So it basically enhances the encoder-decoder architecture by embedding spectral characteristics into this work. We achieved like great results with just RGB methods, and based on that state of the art that we know as for our knowledge, we obtained like great results, and we validated that with a like off-the-shelf iPad Pro. So it's available. Please check our codes, and this on the left is our soccer club in Bucaramanga. We just won the first star, so we are super happy with that. So yeah, thank you. Yes, yes, questions. Yes.
Okay, we have time for 2 questions. This is the question. Okay, go ahead, Jose.
How is this different from the, for example, the segmentation model?
Yeah, I guess they are still constrained. Please correct me if I'm wrong. I think they are still constrained to semantics, not material.
I'm not really sure because they released this SAM for 3D or something like that.
Yeah, they want to segment anything. So yeah, I am aware of the work. We are aware of the work, sorry. But yeah, I guess what makes us different is like, let's move to materials. Let's try to move this new like venue, because I guess semantic is already saturated. And it's very, I mean, we don't have like clusters in Google or this big company. I guess we are screwed. So that's why we are moving to these different like options. Also, maybe instead of spectral information, we are exploring like a polarization or maybe other different domains, such that we can have a chance in this world.
But, sorry,
Yeah.
Do you think it is possible to do some kind of like a fine tuning on the, for example, SAM, and then just compare the results?
Yes, that's actually our current work. I cannot disclose more, but yeah, the goal is to like do some sort of pre-training on that, and then just do like fine tuning on this.
On the materials.
I agree. Yeah, completely agree.
Thank you. Last question, there.
Yes, thank you for the presentation. I think it was very interesting about like this explainability part with the design similarity.
Yep.
I like it.
Okay.
Maybe you're already working on this, but have you considered using like multi-views as input, not just like one RGB-D? It's like a multi-views.
Yes, actually, we started with that goal. I mean, I'm being honest here. We started with that goal. First problem was like processing time. Like when you have like multiple views, like a video, RGB-D video, it's great. We can do better triangulation. We can do actual 3D point clouds. Here is like a 2.5D, as we know. And we are actually considering, but we are lacking resources. I'm looking for nice people to lend me some DPUs. So yeah, but we are pursuing that. I mean, that's the actual, I would say, final goal of this is like.
It would be very cool to have like this kind of materials there.
Mm-hmm.
Then you could use there, but with the multi-views, and then you render the 3D materials.
Yeah, you're reading my mind. Yeah, that's right. That's right. That's the way to go. Yeah.